Okay. Hello, hello, hello? Hello. Whoa. Whoops. Okay. The universe should be in alignment and we should be streaming online. The camera's not tracking me. Is the camera tracking me now? It feels darker and then our time together is cut short, which is very sad. All right, so today what we're doing is talking more about linked lists. In particular, today's lecture will be a bit different. We're going to do more of a major demo. What I mean by that is, so we won't be introducing any new concepts or key functionality. We might introduce stuff if it comes up, but what we're really doing today, and it might seem on the surface to be maybe a less important lecture, however, if you're interested in thinking about the exam that's coming up and the type of linked list questions that are going to be on the exam, especially with the hurdles, today's lecture content is going to be very, very relevant. So is that hint good enough for everyone in the room? Okay. If you didn't get the hint, ask the person next to you. So very relevant for the type of things that we would be expecting you to be able to do with linked lists and the exam hurdles. So not to say that it would be the final exam question, but definitely the hurdles. So when we do the demos later on, when we start, I really want everyone to try and keep up a little bit, and I'm going to bake a lot more time into how we approach the demo, so that maybe you won't have time to write the full solution, of course, but I want us to all think about how we might plan out the solution to the types of demo problems we're going to do. But before we do that, I was talking to someone out the front of the lecture about sort of COMP1511, assignment anxiety, exam anxiety, general progress, and all of this stuff. And I think it's relevant to a lot of you. And we were talking about it sort of with the admin team recently. So I thought just broke something. I just thought to talk about the fact that when you have the comp assignment and you've got your 4 stages, really, if you can do stage 1 and 2, we're happy. Okay? Stages 3 and 4 are starting to get to the point where they're going to be very time consuming and they're going to be very tricky. And part of the reason they're there is to really differentiate between the top 95, 100 percentile of the cohort. Now, not to say we don't want everyone to give it a crack. However, part of sort of acclimating to university life is to sometimes make a judgment call. And should you spend 15, 20 hours on stage 4 of assignment 1 in comp, or should you use that time in your other courses? Having said that, Comp 1511, and actually typically anyway you study intro programming courses, will always naturally take up more time than perhaps your others. And it's just because they're such a keystone course in the progression. But really what I want to do today is talk about the fact that if you're doing stages 1 and 2, and you're putting time into it, but you're making progress and you're understanding, that's a really good position to be in, and you're going to have a good outcome with the exam usually. So I think, did that resonate with a lot of people? They found that the assignments are very time consuming and things like that. It's okay, it's normal, it's intentional. We have a big cohort in Comp 1511. However, when you do invest this time into the course and to these assignments, it will pay dividends in your future comp courses. So I just wanted to try and hopefully reassure some of you, maybe if you're online or watching the recording later, that we know it's tough, and one day you'll look back on COMP1511 and you'll go, that stuff was so easy, I don't know what I was complaining about. It will happen. Okay, another important thing, very important. So we ask for weekly feedback from you in the lectures, and thank you for everyone who's given feedback. We have lots and lots of good feedback. Now, the university is asking for your feedback. Has anyone done a MyExperience report before? If you've done other courses. So, MyExperience is university run, centrally run. So basically every student in every course gets contacted and asked to complete their MyExperience survey. And I know they're really, really annoying, but they are really, really important. Some people that we talk to say, you know, Jake, COMP1511 is a good course, it gets good MyExperience. I had a good time. There's little things that could be improved, but there's no point in me completing the feedback. I just want to complain about Maths 1A maybe. They're going to take me out one day, maths people. But one of the reasons that hopefully you've had a good time in COMP1511, maybe right now you hate us because of the assignments, but one day you'll look back and I think you'll enjoy COMP1511, is because we put so many resources into this course. And if you've enjoyed that investment, please let the university know. It's not just letting me know, it's letting higher ups know, hey, this course is really good. Let's talk to them and see what they're doing. And when we can turn around and say, yeah, it's because we're investing so much into it, give us more money. So MyExperience it was made available this morning. And this is what I was talking about just then. This course does require a lot of resources. Think of all the staffing hours for all the help sessions. And I know a lot of you find that you have to wait for a bit of time to get help with the help sessions. So maybe one of the things you might want to bring up is that we want more allocations for the help sessions. But without the student voice telling us that we want these resources, it's hard for us to argue them. Also, maybe you just had a good time and you want to let the university know. That's nice too. So importantly, they're completely anonymous and cannot be identified. So we have no way of knowing if you completed a MyExperience report individually or what you said or anything like that. And they cannot be associated with your, for example, exam performance or anything like that. In fact, the university doesn't even give us the results until after we complete the exam. And it's run by the university, not the school faculty. So something that we do for fun, so we do get the broad response statistics, so how much % of the cohort responded to the form. So if we get over 70% of the cohort responding to the MyExperience survey, we usually do something fun. So we can change this up if there's other suggestions on the forum, but we can do a bonus stream with some of the tutors, play some games on live and do a Q&A or something like that. We've never hit over 80%, but we can do something really fun if we hit it. But we're also open to other ideas, so please let us know if you have any. But for the first component of this lecture, scan the QR code, and maybe can we get that link in the chat, please? And please do take the time to complete MyExperience for all of your courses, especially 1511. And in the labs, either this week or next week, there'll be time to do the same. So it shouldn't take too long. All right, yeah. I've put it up and I won't roam as much. Okay, how are we going? How many questions are there? Is anyone finished? Anyone need a couple more minutes? No longer being tracked. All right, I'm going to keep going and you can please finish that when you're going. You might even be able to finish it now. Okay, something else, back to linked lists. So I think we might all agree that linked lists are probably the most maybe challenging singular concept in the course. Did anyone agree with that? A couple people. So something else that we've done is in the 1511 teeth, whatever, in the playlist of the YouTube channel, there's a dedicated linked lists animated video that I made, and it's really cool. So it shows like the common linked list code and visualizes how everything's working, all synced up and animated. So if you just go to the YouTube playlist, here, well, the playlist is here. Now we're getting to some inception, and there's this video here, and you can see that it shows off how it's all working, and I even put some code there on the right hand side. The resolution's not good, but it's better in the video. So that's also there as an extra resource for those of you who might want that. I better turn off that so it's not using internet. Okay. So that's just in the playlist on the YouTube channel. So that might be useful for some of you. All right, so like I said, today we're going to just be writing some linked list code, basically. What are we going to do? Good question. Now I'm just wondering if there's anything I can put my laptop on so it's not so low, but maybe not. All right. Okay. So this is the linked list program that we wrote last week. So Sasha started this off and then we finished it off on Friday. And it's going to serve as the basis. Who uses Copilot? It's going to serve as the basis for our programs today. But I will do one more really quick recap of the really important parts of a linked list program, but not sort of everything, so that we can actually get going. And remember, if you're just watching this and you're really confused, you can go back to the previous lectures where it was written. All right. All linked list C programs will start off with our data structure, our node data structure. So it's a struct. It contains the data, in this case an integer. And then here's sort of the important part. It's a pointer to another example of that data structure. So in this case, it's a pointer to a node, a struct node. And what's the name of the pointer variable? Next. Yep, next. Is the audio better online, by the way? Oh, let me know when they reply, please, go. So this is what's going to be our data structure. And then what we have is a bunch of functions that allow us to manipulate and use this data structure to do what we want. So really common ones are printing, for example, where we traverse the whole linked list data structure, but also really important are the ones where we can actually create our node and insert data into the data structure. Right? Do we want to look at one of them? Or who's ready to just start with new stuff? So can we who wants a recap of some functions? Put your hand up. And who wants to just keep going? I think the recaps have it. We'll do one recap and see how we go. Maybe let's look at create node, because I don't think we looked at that on Friday. So create node's a really good one. Its job is to take some data, for in this case an integer, because that's what the data is in our struct node, and a pointer to where we want to place that node on the heap. Make the code. The week, it's in the right folder. So, hold on. Can you try that? But is the week 9 hooked up on the course page? What if I Teams it to you and then you can put on the forum? Okay, hopefully we haven't. Oh. And then hide all my secret messages. Okay, so Gab will put the starting code on the forum. Good point. Thank you, Gab. Okay. So this create node function, what it's doing is it gets given some data that it's going to put into a created struct, and it's doing this through the malloc function. Why does it need to use malloc? Can someone tell me? Why do we need to use malloc here? But we could have just created a struct and put the data into it, right?
But it's not. So I need to save some data for it.
But why specifically malloc? You're not wrong, but there's a... We want to save it on the heap. That's right. The reason we want to save it on the heap is because this is a dynamic data structure and we want it to exist as we call and exit other functions. That's right. So whenever you see malloc, guys, remember just the murmuring because it gets picked up on the mics really easily. Whenever you see malloc or realloc, what should you think? Heap. Heap, heap, heap. It means the data is being put on the heap. Another thing to think is that if you malloc data on the heap, what also must you do at the end? Free it. Okay, I think you should have covered realloc in one of the lectures, but realloc is very similar to malloc, but it gets given an existing heap allocation and resizes it if it can. All right, so we've malloced this node called new node, which is going to be on the heap, and we've got a pointer to refer to it. Then what are we doing? We're storing this data that was passed into its field on the heap, and we're saying that this next node is going to be hooked up to it. So this next node is going to be placed after the node that I'm creating. And then we return it. We return the address of it. So another thing just to think about, whenever we call malloc, what do we get back?
A pointer.
Yeah, a pointer. Malloc returns a pointer to the location on heap where that data structure was, or that memory was allocated. All right, let's look at one actual linked list function.
Deleted position.
Sorry?
Deleted position.
Deleted position. Let's look at, we wrote that on Friday. Let's just look at insert at location maybe. So insert at location, in this function we're given the index or the position in which in our linked list we want to try and put a new node. So that means we need the data that we would like to create. We want the location itself, so where in the linked list positions we want to insert this, and we want the actual linked list, the head to the linked list. In this function, if the linked list is empty, well, we can't insert at a position, so we just return null. We create a reference, a local variable, which also points to head, which we can use to traverse the linked list. And we have a counter that can count how many times we've done that traversal. So while we still have data, while the current node that we're iterating over is not null, we can check, hey, have we managed to iterate enough to the point which our counter and our location is the same integer? Because if it's the same, it means we're at the position in which we want to insert the new node in position. Does that make sense? Because this loop, every time it runs, is what's doing the traversal. So it adds one to the counter to show that it's iterated, and it moves, sets current to be the next to the next.
If you add to that function, where it would still make a node even though it's an empty list.
You could absolutely modify this function. So the question was, could we modify this function to support an empty list? And the answer is absolutely. But it is up to you to think about what does it mean to insert at position 3 with an empty list. Does that mean you just put it in? Or does that mean you shouldn't put it in? You should only add it in if it's at index 0. So this is where there's no right or wrong. It just depends on what your library should be doing. And in this instance, if the list is empty, we're saying, well, it doesn't make sense to input at any position. If we are at the correct position, so we've managed to iterate enough points, enough elements. We use this create node function that we just stepped through with the data that was passed in. And we set next of this new node to point to where we previously were pointing to, because we've intercepted and now we've hooked it up there. And we set the previously current node to point to this new node. So this, and we did a whiteboard of this last week, but it chains up the new node in the correct position, and we return head, regardless. If this is confusing you, I really recommend you watch that video I just showed you in the playlist. There's some nice animations, and you can slow it down and try and get your head around it. Okay. So what are we going to do today? We're going to do a few things. Let's clean up the code a little bit. Thank you, Copilot. We're going to add a function called weave lists, which sounds really cool. We'll talk more about what that means. And then if we get time, we're going to add a function called max of pairs, which we'll also explain. All right. So let's just clean up a little bit first. This is all pretty fine. This is all pretty fine. I just want to clean up this. So this is when we described command line arguments. So I'm just going to delete that stuff. Keep it really nice and simple. And I'm going to annotate a little bit. So here we're creating a really simple chain of a linked list, and the data is going to point 1, 2, 3, 4, 5. And remember, because of the way these get hooked up, the reverse order is the order in which they're created. So to prove that, we can print it there. I'm going to delete this and really just delete all of that. And so what we should see here is 1, 2, 3, 4, 5 pointing to null. Cool. So really nice and simple. All right, weave lists. Let me demonstrate to you what I mean by this. Once this loads. Go away. Okay, so here are two linked lists in the heap, two different linked lists, right? So which means there's probably going to be two head pointers pointing to them, right? In main. Two completely separate linked lists, and we want to weave them together. I got to stop leaving the MacBook for the mic. Is that what's me again? Yep. Useless. Yeah, AI is going to take over the world for sure. So we want to weave them together. Well, what do we think we mean by weave? So we're going to make a new linked list, and maybe I'll color them. These look like crap, but so it means we're going to make a new linked list that's going to start with item A. It's going to point to the first element of list 2, which it's going to point to the second element of list 1, right? You get the idea? And so on and so forth. So we're literally going to be weaving two linked list strands. You might be thinking, Jake, what an insane idea for a function. There's no way that this would ever be useful in the real world. You could imagine where you've got two lists of priorities where you need to process things, and they've both been sorted, and now we want to make it fair, so we want to do one at a time. So we merge them into a single queue that we want to process things. So actually, there could be real world use cases for a function like this. And I want to reiterate again, something like this might be a pretty reasonable second linked list hurdle. So the more complex of the two. But does everyone get the general idea? All right, good. Now we need to think about implementation. So rather than just jumping in to write some code, why don't you all take a minute, if you've got maybe pen and paper, or just your phone, the Notes app, or whatever, you can turn to the person next to you, or you can do it on your own, and write down how you would approach something like this. What do you think the steps are, the pseudocode for a problem like this? So I'll tell you now, you're given two linked lists. You don't have to worry about what's in them. And so let's say there's head 1 and head 2, and head 1 will go first. So what that means is that this was head 1, for example. So don't worry about that, but given that function, what steps will you need to go about solving it?
What happens if head 2 is less than head 1?
That's a great question. So do you want to say the question louder and then I'll repeat it?
What happens if head 2 is less than head 1?
Okay, so the question was, what happens if one of the lists, let's generalize it, is a different length than the other? And this is exactly what you should be thinking. There's actually, because you need to know that in order to solve it. Now, in the exam, we will tell you these edge cases. So let's assume, we even call them assumptions in the exam questions. Let's assume for now, they are the same length. Later, we'll modify it so that we don't have that assumption. But for right now, when you're doing this, assume that they're the same length. That's another good one. So the question was, what if one of them's null?
Well, I mean, you've just said that both have to be the same. So
Yeah, but they could both be null.
Yeah, that's what I'm saying.
So let's assume not null. But again, I think we can modify the code to later on, once we get the basics done, to then handle that case.
Well, sorry. Like, can't you have like a 2.2.1 where like when one list isn't the same as the other, you can still do that. It's just when
You can absolutely still do it.
but if it's like n and then n plus 2, then you're screwed, right?
Well, let's just for now assume they're the same, and then we'll handle all these cases. Have you done it?
Absolutely not. Working on that one.
Maybe once you've written down some steps, which either you're not doing it or you're very quick, maybe you could then turn to the person next to you and compare your notes. And maybe just throw your hand up briefly when you're ready to look at implementation. Sorry, I shouldn't have done that. Is that a question or are you ready?
I have a very brief
Idea? Let's give people a second and then we'll talk ideas. In fact, if you're really brave, someone might want to come down and actually implement it. You want to do that? Okay, let's wait a second. Last time, though, this happened last term, we ended up throwing all of his code away. But he became a tutor, so... Is this stop tracking me again? What's going on with it? Oh, God. Whoa. I can't deal with these things. So there was a question, while you guys are still doing that, there's a question online that Gab has answered, but Naveen asked, why do we only work with linked list on the heap and not in main? And Gab said one of the reasons is so that we can have access to the data once a function ends, which is absolutely correct. The other reason is we don't know how big the linked list will grow, and the stack frame is limited as to how big it should be when we create the function stack. Does anyone have, so before we get to you, does anyone have a general few steps they want to just read out?
Well, like in the code?
Not in code, in just pseudocode, but let's give someone else a chance first and then we'll...
I have one step.
Okay, yeah. Weave them, yeah. Anyway, go on, yeah.
We can make a counter, and then when it's odd, you add an element from one list, and when it's even, you add an element from the other list.
Okay, so the general idea, let's call it here, was that have a counter, and if it's odd, pick A, if it's even, pick B, something like that. Did anyone have this idea of a counter? You did? You did? You did as well? Anyone else got a completely different solution? It might be a good idea to have a counter. I haven't thought about it.
We would have two buffer structs.
2 buffer structs? What does that mean?
Like temporary, just a hold value temporary.
Yeah, and then what?
And then like for every current value of every list, we temporarily assign dot next to the buffers dot next, and then we point the first dot next to the second list's first one head, and then the same thing for the second.
So you got list 1 and list 2 in the heap, and then you're making a new temporary one in the heap, and then making, do you have a third linked list?
No, we have two linked lists, right?
So are you modifying them or making a new one?
So we have two heads, right? Head one and
Yeah.
head two. So the next value of head one, we save that in one of the buffers.
I'm not quite seeing it. Not to say that it's not right, but but I would have to see it more. I can't see the solutions not jumping out.
I'm asking the question again, sorry.
So I was just asking, what is your general solution?
Well, for the while loop, if you're bouncing between, say, list A and list B is always going to be the second week, right?
Yep.
So if you kept bouncing back and forth, you could say while list B is not equal up, and then keep going until list B.
And what about list A?
Well, I guess it doesn't matter because it's the loop word if B is.
Okay, so you're saying that because we've assumed the list's length are exactly the same, we can just loop through one of the... That's actually pretty clever. It's not the solution I had, but it would work. But I guess this might be unfair to say, but later on we're going to assume that they're not the same, and then your solution would fall apart. But it would work for this case, and that's completely fine.
If they're not the same, we first work out which one is bigger, and then we apply the same thing.
Interesting, we'd have to work through some details. Okay, so there's a lot of different ideas, which I think proves point number 1. There's no single solution to this. There really isn't. There's lots of solutions. So we'll write up a solution together, but if it's not the solution you came to, that's not the end of the world. Did you want to have a go at writing a solution?
I don't trust my typing.
Okay. It's hard, I know it's hard. Do you want to have a go? Okay, come up.
Obviously, I've been tested because
That's okay. All right. So let me get started for you. So what we're going to have here, and if you're typing along, you should maybe start writing your solution too. So we're going to return whoops, what am I doing? We're going to return a pointer to a linked list, which is the new weaved linked list. It's going to accept two linked lists, head 1 and head 2, and we are going to forward declare the function just so we don't have any issues there. And then I guess the rest is up to you. So everyone, remember, trust me, when you come up here and you write code, you lose, I reckon, about 50 IQ points instantly. So let's be gentle, come on. All right, give it a go. And it's a longer function, so you might not.
But I have my reference.
All right, go.
Okay.
And we can all help out if we get stuck on actual implementation. All right, so first thing, let's see what's happening.
We already have node head 1 and 2, so current 1.
Yeah. So it looks like we're creating a new linked list called head, and then we're creating the two iterator linked lists called current 1 and current 2. That looks okay to me. Just let it. Oh, there's a typo there, but
Oh yeah.
the autocomplete is slow while I'm streaming.
Yeah.
All right, nice.
Alright, now that we have required.
Okay, so it's probably time to iterate now. Oh, a for loop. Okay.
Less than 2 times. What's this size
Okay,
function?
interesting.
Size.
Size of linked list. There it is.
Takes in the struct head. Okay.
So what we're doing here is let's look at this.
Right.
So looping over from 2 times the size of one of the linked lists. Oh, I see. Okay.
Yeah. So
Who knows what that operator is on line 42? Modulus? Yeah, so it's checking if it's an even number.
insert a tail. Alright.
Okay, so let me just describe this as it's being written. So he's looping. What's your name again, by the way?
Omran.
Omran?
Yeah, Omran. O-M-R-A-N.
Omran.
Yeah.
Okay. Omran is looping for the amount of nodes that should be in the new resulting linked list. That's why it's 2 multiplied by the size of one of them. Right? If it's an even iteration, he's creating a new node and putting it. Okay, so if it's an even, he's taking the data from list 1 and adding that to our new linked list called head. And then I think we're going to have an else statement here. Insert into
Is it Command C or Control C?
Command C. Command C. And we're going to do the opposite, yeah.
Yeah. And then after that, I suppose we just
Return.
oh yeah.
Yep.
Sorry.
That's okay.
Yeah. Dun.
Does anyone have something similar to this? No?
Return
Head.
Oh, I think that's it.
All right. Round of applause, everyone. Well, I guess we should test it first. I know, I'm kidding. All right. So the way I'm going to test it is I'm going to make two linked lists like that. Does that make sense to everyone? So I think we should see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 if it all works successfully. No error, that's a good sign. Okay, 2, 1, it looks close, but I think they're out of order. I'm assuming that's going to be, so I starts at 0. Yeah, I think so. Because 0 mod 2 is false. Yeah.
So just not
It needs to be double equal to 0.
we could not
If it is equal to 1, which is meaning that it's odd.
I think that should solve it, right? No?
This will stay the same because either way it's going to be initially 0. So we just noted so that 0 comes 1.
Okay, look at that. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to null. Cool. All right. That's really good. And this would be if you can do something like this, and obviously you've got a few more weeks to practice, you're in a really good position. Let me talk about maybe how I would have solved this. Not to say there's anything wrong with it, but well, I can point out a few things I think that we can improve this solution with. What time is it, by the way? All right. Number one, something I want you to think about. I shouldn't leave. We used size of here, right? What does size of do? And how does it do that? So size of here needs to iterate through every element of the linked list.
Every time.
Every time. Every time. In fact, yeah, that's right. Every time we run the loop, actually. So there's definitely some efficiencies we can perform here. I mean, obviously we can pull that out into a variable, but even then we don't need to do it. We don't need to get the length of the linked list because we're traversing anyway, so we can check it as we go. So that's one thing. The other thing is that this solution does restrict us to the case where the linked lists are the same length. Right? So what if, like, we go back to this assumption that they're not the same length? Then this solution won't work. So if head 2, and we can actually just prove this, goes 12 and then 14, we might expect that to be part of the weaved solution, right? Because it's still weaved, it's just there's nothing to weave it with. So what do you want to do? Do you want to do break now and then come back and I'll do my solution and then we'll do a Kahoot? Does that sound good? Yes? All right. 5 minutes, 10 minutes. Stretch, coffee, bathroom. Then we'll come back. I'll show you how I solved it, but very good job. And then we'll do a Kahoot.
I was going to mention that when I worked on the list before, we used to use two slides of classes, one which is known as self, and then the other which is the linked list. And the linked list will contain the head node.
Yeah,
And
yep,
then
yep.
you also have a variable for the size, which will change depending on if you're depending on popping
Yep.
nodes away. so that could counteract the grouping for the entire.
Yes, that's right.
Yeah.
Was this Java or something?
I did like.
Yeah, so typically in those sort of languages, we value niceties like that over memory allocation. So this uses slightly less memory. That's the short answer.
Yeah.
A length function like that you would not typically see in like a standard library. It's a better data structure the way you're talking about it. Yeah. But to teach traversal, it's a good way of doing it. But yes, I'm not criticizing your implementation. Yeah. It's fine. Yeah, it's a good point. Yeah.
How much of the allocation methods do we have? We have malloc and reloc and calloc. Those are
Yes, that's right. Do you know what calloc does?
yeah, it's like.
Is it on the slides? I can't remember.
Because I don't remember that we took calloc and reloc, so it just was about calls.
Okay. Hello. All right, was that about 10 minutes? Yes? All right. All right, do we want to see how I would solve this? Yes? No. Neither. All right. So here's what I would do. I would keep it really simple. Do the exact same thing here. Maybe we can call this result, just to be really, to be a bit more clear. The only reason I'm doing that is because we've got head 1, head 2, and it can get a bit complicated. All right. Rather than using the size of the linked lists to know how much we can iterate, we can simply loop while and so while both of the iterators aren't null. So at this point, it will still assume that they're the same size, because as soon as one of them has reached its end, the loop will stop. Does everyone see that? Yeah. But there could still be data in the rest of one or the other. So while there's data, all we're going to do is say result . Well, in fact, I think we can. No, let's not do that. So results will, when we start off,
Use our existing function.
yeah, insert at tail. I think we'll do that. And I think that's actually it. Oh, yeah, sorry. Yep. Here?
It means that we have to change the color to next.
Oh, yeah. Yep, thank you. Yep. Something like that. I think that should do it. Shall we just test that out? So just some quick benefits. We don't need to count the list, which means we don't need to traverse through. And we don't need a counting variable either. All right, but let's just test that it works. One, two, three, four, five, 6, 7, 8, 9, 10. Nice. All right. Now, the other benefit of the approach is that if we did want to support different length linked lists, this approach would be a little bit more work. And we actually have a pretty cool way of solving this here. So let's think about what's happened. We've iterated while both our linked lists aren't null. So for this to fail, we're now at a point at which one of the linked lists is empty and the other has a bit more data. So knowing that, we can really simply say, while current one is not null, so if there's data on the first list, add it to the end of result and consume all of it. Or maybe there was no data on current one, maybe it was on current two, at which point iterate through current two. Does that make sense? Okay, that didn't work. Wasn't there? Help me out here.
Did we modify the elements? Is it like the new values inside the two? Did we modify it, or is it still 1, 2, 3, 4, 5? Still 10.
1, 3, 5, 7, 9, 2,
Oh, yeah, there is a
10, 12, 14.
But we put null. We put null. Did you scroll up? Yeah.
Oh,
Between
whoopsie.
null.
Yep. Thank you. Yeah, cool. And you can see it's gone 6, 7, 8, 9, 10. Then linked list 1 ran out of data, and it went 12, 14, consuming the rest of linked list 2. Let me just leave that here for a second so people can look at it or ask some questions. Do we have any questions on this? Yep. Guys, the noise please so I can hear the question. Say, sorry, which line number am I looking at? 9. Because it's the last one. It's the first one. It's the head, so it points to null. It's the final element in the list that we're building. So what would its next be? It's next. If we look at create node, that's next. Because we construct them back to front. Does that answer your question?
Now I've got 2, but why then did it work when you didn't put null? You just changed it from head 2 to null.
Because when it was null, it thought that that was the end of the list earlier than it actually was.
No, it was head 2. Like, yeah, on line 33, it was 14 head 2, but now it's null. Why, when it was head 2, did it work?
Because it is set to null. The value is at
No, but it was head 2, he's saying.
yeah, line 23, 24. See line 23, 24?
Oh, well, right.
Yeah. That's okay, yeah.
And then, why do we use the inserted tail function?
Because, I think we could have used create node actually. It's because we're placing it at the end. Tail is the end. Because we're constructing a new linked list. So results got some data in it, and we're weaving, and we don't want to put it here. We want to put it at the tail.
It's just on the drawing we did, you were doing it like.
It's not quite. Yes. Okay, I see. I didn't. It's not quite working in the way that I did it in the drawing.
It's all back to front.
Yes.
Yeah. Okay.
So let's see what it really did.
Yeah, that helps.
Let's think about it. So it starts at the front and it says result equals the first data. No, it is doing it like that way. So result is that one. Then add 2 to the tail of results, which is this one. Then it goes forward 1 and it adds 1 to the tail of result, which is this one. Right? Any more questions? Online, any questions? I use Figma, that's the diagram software. Okay, cool. All right, Kahoot. Oh, it's here. What is this music? Oh no, it's the same music. We can change the music. Brain next is 0. This camera sucks. All right. We ready to go? See hater. You guys stress me out. That should say T3, ignore it. What is the correct way to copy a string into a linked list node? Can you read that? Oh, very good. That's excellent. Did you do this one already as well? Have we done this already? No, you're just really good. Why is it green? Someone just yell it out. Yeah, because you can't assign strings in C. You have to use string copy, and you also have to know that it's an arrow for a struct. I'm really impressed with that, actually. Good job. Very food-based leaderboard so far. Where does this linked list stop? I think we had a similar question last week. All right, so 32 of you miserable souls put second last node, and I think, I'm joking by the way, I think what you've thought is, let's just think about this. While the current next node is not null, will fail when we're at the node when there's data at current. Does that make sense? And so the loop will fail, we won't iterate, and current will be the last element. Because its next will be null. So think about it. What will the last, what will current next be? If you put second last node, if it's the second last node, next will have data. It will have an address. Because it'll be the last node. So if you wanted second last node, what would you need to do? Current next. Exactly. Does that clear it up for those of you who put green? You're just too embarrassed to say? All right. All right, 50-50 shot. Can you create a linked list without using malloc? Oh, that's brutal. That's brutal. All right, who put true? Put your hand up and keep it up if you didn't guess. Do you want to say why it's true? Yeah, there's nothing stopping you from doing it on the stack. However, it defeats the whole purpose of linked lists because you can't grow it. Because you're out of room. You've defined how big your linked list will be at compile time, right? So stacks can grow, but they're set to the size at which they look like they'll need to be at compile time. So you'll almost never see it, but you can do it. Good stuff. All right, we lost someone. Another true or false. Linked list nodes must all have the same type. Linked list nodes, so the element in your linked list must have the same type. True or false? That's brutal, that's brutal, that's brutal. Okay, once again, did anyone put false and not just guess it? Let's let someone, who put false? Someone had to. Do you know why you put false?
Yeah, because nodes connect to each other by pointers, which are just recursive.
Okay, that's a great answer. All right. So the reason why it's false is because what mechanism do linked lists use to point to each other? Pointers, addresses. And could I have a next pointer point to a bit of memory that is of a different type than the current element? And the answer is yes. And actually, you might think that this sounds quite academic, but you could have in some instances where this is useful. So for example, the payload, the data, could be a max size, so that when you point to the next node, it could be different types there, but they're always the same length, so it knows how to read them. Or there's a concept in C called unions, which you maybe haven't heard of before, but unions let us have, for example, a linked list of different typed nodes. So it is possible, but it's a little bit more advanced. But the reason why you should have been maybe able to get there is to think that, well, why couldn't that next pointer just point to something else? And the answer is it can. All right, last question. What does this program print? Oh, this is a good question. Okay. So most people said 36. What was the reasoning for 36? Can someone illuminate me? So I think, now I've got to double check this. But can someone quickly check this actually? Who's quick at typing? So it's getting the size of no. Yeah, it's definitely 8. It's the size of a pointer to a node. And pointers are always 64 bits or 8 bytes. It's not the size of a node, right? Which would have been, I think, 8 plus 8. Which is 32. Is that why you were saying 32?
No, it's going to be 40 if it's going to consider the nodes approximately, right?
It would be the size of a pointer plus a pointer.
Yeah, but isn't it the struct node is going to say the size of the pointer and the string?
But the string is a pointer. Remember, arrays are the address of the first element. Yeah, that's right. That's just to throw you off. Yeah, that's right. Did that answer it to anyone else that didn't quite understand? So really, this is asking what's the size of a pointer to a node. All right, who's on top? Nice job. Manish Latte, is it? Jan and Savika, come on down if you're in the room. Are you in the room? Is someone being shy? Are the rest online? Who's Manish? You're Manish? Are you all three of you? Are you serious? That's a cartel. They really hedged their bets. They went all in. All right. Who's Manish? Okay. You take your first pick out of the 6.
You gotta take the numbers.
No, numbers. You gotta go for the drawing.
I think this will look good.
All right, good. Show the camera maybe if you can. All right, congratulations. Who's Jan? Okay, you get second pick. Selected by third pick.
This one.
That's a good choice. All right, congratulations. All right. Stop sneaking up on my Spotify played history. I saw some of that feedback in the lecture feedback last week. It was so funny. All right. Or actually just send me like new suggestions, then I'll listen to new stuff. Okay. All right. We did say we would think about not null, but the answer is really simple. Yeah, in fact, I think all we need to check, in fact, actually, I don't think we need to do anything. I think this handles if one of them is null, but we can test that. So this should just print 2, 4, 6, 8, 10, 12, 14. Yep. And this should just print null. Yeah. So they already work. So the reason they already work is because if they're both null, this fails, right? And so it would just return result, which is null, which makes sense. If one of them is null, this whole thing would fail, and the other one would be added on. Just the way it works as to when we've consumed the pairs in both of them. So actually that was really easy.
That loop wouldn't fail though.
The first loop,
Yeah, it's in front row.
if they're both null,
No, one.
the whole thing would fail. It would never run.
Isn't it if they're both null?
But if the first one is null,
Yeah, then you check.
then you don't even check the second condition because it's ANDed. They both need to be true to run the body. So if one of them's false, we don't run it. This is actually really, not to toot my own horn, but an elegant solution to this problem. When something like that happens and your solution here already covers the edge cases, that's a rare moment where you're like, okay, this is actually looking pretty good. All right, well that was easy. Is everyone comfortable with the weaving? Okay, the other idea I had, what time is it? The other idea I had was in fact, I think this is a past exam question that I just completely ripped off from the exam body. But obviously, I'll try to make sure we don't do it this year. So this function is going to be sort of similar, I think, but take max of pair. So,
Maximum
sorry?
scalar return is struct.
No, so the idea here is iterate over two linked lists in pairs, create a new linked list with the larger of the two pairs. So you've got, so it's a little different. We're not weaving, but we're saying here's a pair. So two linked lists here, the top row and the second row. They've got an integer in them. One of them will be larger than the other. Pick the larger one, and that goes in the new linked list. So for example, maybe green was larger, so we would cherry pick the green out. Maybe this one was larger, and maybe this one was larger. So that's what our new linked list would be.
So the sizes of the two arrays now have to be.
Now let's completely assume that they are the same size. Again, in an exam context, we're not trying to, stress you out and get you. We would tell you what to do in these edge cases. The other edge case we need to deal with here, if I'm just thinking, is if they're the same value.
Would you care about the pointer or the value itself?
Well, hold on, let's finish this train of thought. So if they have the exact same value, again, we would tell you what to do. What's a reasonable thing to do? Maybe just we'll just take it. Take the value.
Take the first one.
Take the first one.
Or if it's like you can't take a match, like there's no pair, there's only one, then you just return what the
No, so yeah, another assumption that we'll make here is that there's always the same amount. And this is what I mean by in the exam, we're not trying to get you on these little details. Sometimes people really stress about that. There won't be something like that. we will tell you up front if there's an assumption that we are making. All right, so the good news is, I think, that the solution is there's some similarities here to the weaving, right? We need to loop over a pair of linked lists and do something for each pair.
Could we just copy the code for weave list and modify?
We absolutely can, but maybe just for the sake of it, let's rewrite it. Yeah, but that's what I would do typically. I will copy this part actually. All right, let me just remind everyone what we're doing here. Whenever we have a linked list, we need an iterator or a pointer that will store where we're up to. And because we have two linked lists, we want two of them. And they both start off at the head of each linked list. Yep? We will then have our results linked list that we define here starting off at null. Let me give people a second to type that up. Let me know if you've caught up typing. Let's think about what we can do here. We need to iterate, and in fact, iterating is going to be the exact same as weave. While we've got data in both of our linked lists, we'll keep going through. So yeah, let's actually keep that. So while current 1 is not equal to null and current 2 is not equal to null.
We need to test a non-possible edge case.
Well, let's do edge cases at the end. So while there is data in both pairs of linked lists, as soon as one list is null, we stop looping. Right? That's the way to think about this type of traversal. So let me go back to the whiteboard for a second. What we're doing here, we've got two linked lists. We're starting off at this point. Current points to green, current 2 points to yellow. While there's data here, eventually we'll go on to the next one, go on to the next one. Oops. And we can do something for each time. Now, what is it that we want to do every time we loop?
Compare the data.
Compare the data, compare the value of the data. So I think what we can do here is say if current 1 is greater than or equal to current 2, result is going to equal to insert at tail. Whoops, that's not right. Thank you. Let's think about that. If current 1, so if the value in current 1 is greater than or equal to that in current 2, which means that if they're equal, we will still get the value, add to the end of result that data, that value. Are we done? We need an else. And what do we do in the else?
Basically just results equal to insert at tail current data.
Yep. So I'll just copy that, but we use results too. So if add it instead. So if you notice in the weaving, every time the loop runs, we're adding 2 elements to the new linked list. In this one, we're only adding one or the other, depending on if it's bigger.
But because of the assumptions we made, we don't need greater than or equal to, right? Because it's not actually correct if you return the first one where you could return. As in, like,
We do actually need the greater than or equal to, because if it was just greater than,
I mean, it's going to go to the else, so it doesn't.
oh, it would be the same thing. Yeah, you're right. Yeah, that's right. It's the exact same value. It doesn't matter. Yeah, it doesn't matter. I think that's actually it. And then we just return result. So everyone, please, the noise. We're almost done. Say that again. Current one. Oh, I haven't iterated. Thank you. Thank you, thank you. Yep, that's what you meant? Thank you. All right, shall we test this out? So we've got two linked lists here, head and head 2. That's weaved. Let's take the max. And print that. What do we expect to see here? Let's think about it. So 1 is 2, 4, 6, 8, 10, 12, 14. 1 is 1, 3, 5, 7, 9. I think it's just going to be 2, 4, 6, 8, 10, 12, 14. Because that's always bigger.
14 and 12 are not included because
They won't be included. Oh, there's an error. Did I forward declare it? Probably not. Line 44, there's a warning that we're not using weaved, sure. Let me just... Yeah, 2, 4, 6, 8, 10. Again, I would say, everyone, this is about as tough as the linked list hurdle 1 would be. Something like this.
So exam is composed of 2 questions, right?
So just to clarify with the exam hurdles, because some people do get confused about it, there's 2 hurdle topics. Come on, everyone. Guys, there's 2 hurdle topics. One is pointers. Sorry, arrays. Everyone's very excited about murmuring what they're murmuring on. One of the hurdles is arrays. One of the hurdles is linked lists. There's 2 hurdle questions per topic, an easier one and a slightly harder one. And you only need to get one of both complete. So you only need to pass one of the array hurdles and one of the linked list hurdles. Doesn't matter which. So basically the way to think it, you've got 2 chances per topic. Guys, please, I can't hear the questions.
So there's 4 hurdles. How many of that is, like, what percentage of that is, like, the total of the actual?
I can't remember the total percentage of it.
But this is not the whole exam.
No, there's way more to the exam.
Yeah. It's like multiple choice questions.
There's no multiple choice questions. There's some debugging questions, and then there's code writing questions. We'll have an entire exam revision. I just wanted to point out today that this is about, if you can do something like this comfortably, you're in a good position. And if not, go through this yourself and set similar topics. Take minimum, for example, take average. Come up with your own practice versions and even test each other out and see what solutions you get. And remember, there's more than one solution and there's partial marks. So you don't need to get it fully complete. You might just show that you're really close but had a syntax error and we'll still give you the marks. Sorry? It depends how big the logical error is. If it's a fundamental problem, you might not pass it. If it's a small detail, it's probably okay. All right. I get the impression that everyone's sick of hearing my voice. So let's wrap it up there. Oh, I don't have the lecture feedback. Okay, no lecture feedback this week. Please do your MyExperience. Please, please, please. We're going to hammer on about it. Let me see if there's any questions online. Yeah, so there's auto tests for all the questions that you get access to. So you can see that you're doing it right or not. It's really similar to a lab exercise. However, I will point out there's no DCC help in the exam. There is DCC, just not DCC help. There'll be edge cases, and there'll be secret tests, yes. All right, thank you all so much. If you're online, thank you if you came. I'll see you Friday, and then it's week 10, our final week together. Yes, there's man. The exam is 3 hours unless you have a learning provision, and that can be longer. Oops.